So the first major concept here is the concept of energy. Energy is a very generalized concept in physics, and it's basically just the capacity to do work. And what's that mean? Work is basically taking any physical object and moving it, bending it, crushing it, building it, breaking it, moving it. It doesn't matter. That's the concept. Okay, so if we can't move something or build something or break something, you would say there's not enough energy to do that. Okay, so there are different kinds of energy, and we'll go through that a bit. So first of all, you can divide all energy into two basic categories. You probably learned this back in maybe third or fourth grade, the idea of kinetic energy and potential energy. Okay, but as an adult, you can now kind of refine your concepts here a little bit. Potential energy is basically the pure energy. It's the energy that's not being used at the moment, but you can use it when you want to. This is the energy inside a battery. This is the energy inside a mousetrap after it's been carefully coiled up. It's the energy behind a dam in water. It's also the energy within chemical bonds, like within sugars or proteins or fat molecules that we eat. Kinetic energy is when you take that resting energy, that stored up energy, the coiled spring, the chemical bond, and you release it. And now it starts going downhill. It always goes downhill. Energy is always falling from a high energy state to a lower energy state. Okay? And if you think about it, as that energy is falling downhill, you can put some of that energy to work by going uphill. And that's basically how the cell operates. It takes energy from organic molecules and it breaks them apart. And in that high energy state, it falls down to a low energy state. And in that process, we build things, we move things, we live. Okay? So all energy is divided either into the kinetic or the potential types. Okay, so when we talk about chemical energy or mechanical energy or thermal energy or solar energy or the energy of a spring or the water behind a dam, all that, you can put each one of those types into one of these two categories. Okay, and the one we're going to use the most is chemical energy. And so chemical energy is a form of potential energy. Okay, so now we can think about the way we use energy on Earth. Okay, all of life is ultimately driven by the sun. We call that solar energy. Right? Solar energy is just photons of a certain wavelength shining down on Earth. And as that energy hits Earth, we have the first layer of life we call the producers. These are the algae in the ocean or in the lakes and streams. These are the trees. Sometimes there's bacteria, cyanobacteria. All of these photosynthesize. They use light to make high energy organic molecules. And so in this diagram here, you can see that the plants are making high energy molecules like sugar. And you can see here the moose eating them. And so you can see chemical energy right there. Chemical energy here would be the sugars that the moose is eating. And then what the moose does is he changes that energy from its potential form to a kinetic form, into mechanical energy. Okay, so there we go. Here I got my laser pointer now. Okay. So one of the key points here is you can't recycle energy. Once energy is gone, it's gone. It flows downhill. Now, when I say gone, I don't mean destroyed. I mean it was converted from a useful form to a less useful form. Okay, so that's like converting the energy of the gasoline in your car to mechanical energy, but some of that energy is put out as heat. It's wasted. So this idea of energy flowing downhill and not being able to go back uphill, that's your second law of thermodynamics. That's the hard one. Okay, the first law is the easier one. That just says that we can't make or break energy. We can't make it and we can't destroy it. All we can do is convert it from one form to another. So think of the universe itself, everything we know. That's a system. And within that system, there's a certain amount of energy and we can't add more to it and we can't take any out. So we call that a closed system. All right, so some examples of this. You have leaves that photosynthesize. Okay, they take the energy of the sun and they make some sugars. And then in turn, the moose will eat that leaf and he'll use that to move around and live. Okay? Every single time energy is converted from one form to another, from chemical energy to mechanical energy, for example, a little bit of that energy, or actually most of that energy in a lot of cases, is lost as heat. Heat is just the transfer of energy that's not useful from one place to another. Okay? And so remember, if you recall Brownian motion, that's the idea of every molecule in the universe is jiggling just a little bit, a little vibration. That vibrational energy, we call it thermal energy. It's not useful. You can't do much with it, but everything has it. So that's that version of useless energy, so to speak. And so every single time we change energy from one form to another, some of that energy that was changed gets converted to thermal energy. Okay? All right. So the definition of heat here, when they say heat is released from cell respiration, that means that some of that thermal energy is wasted. Or rather, some of that energy that's released from cell respiration is wasted energy, and we call that heat. Okay, so another way to think of heat is just not useful. It's not useful energy. This is why we have a body temperature, if you think about it. Okay, the reason why you're warm right now is because you're burning down organic molecules, and you're using some of that energy to live, but a lot of that energy, I would say about a little less than 70% of it actually, is not being used for anything useful. Okay, so this concept of moving from a high energy state to a low energy state, from a highly ordered state to a less ordered state, everything flows downhill. Okay, this concept is entropy. If this is confusing to you, just replace the word entropy with the word disorder or chaos. Okay. All right, I'm just reading this slide here. It says that every process that occurs in the cell increases the total entropy of the universe, right? So in general, the general rule is in a closed system like the universe, you can't go uphill. You can't overall increase the order of a closed system. You have to put energy into something in order to increase its organization. Okay, now within that huge universe, of course, there are many systems. And so you can think of Earth as one system. Earth's an open system. Why is it open? Because the sun is continually giving us new energy. And so with that energy, what we do is we can go uphill a little bit. So we can decrease the disorder on Earth. You can think of that as decreasing the disorder locally within the universe, okay? But ultimately over time, that will increase the disorder in the universe. As life wears out and as the heat emanates back into space, everything does eventually go downhill. But with that energy coming in from the sun, we can go uphill, and that's where life comes from. That's how evolution works, by this constant input of energy from the sun. And so here's a simple concept. You can take glucose. Glucose is a 6-carbon molecule that's highly ordered. So you would say this molecule has lower entropy than this system of molecules, right? So another way of doing it, here, let me get my pointer to get a pen now. This is system, wow, that was a little silly. This is system 1, okay? And this is system 2. You can think of it that way. So system 1 and system 2. And forgive me, I'm writing with a mouse right now. System 1 is highly ordered. System 2 is less ordered. System 1, therefore, has lower entropy, less disorder. And system 2 has more disorder, more entropy. Over time now, you can see systems tend to move towards a higher entropy. This is just an intuitive way of saying everything goes downhill. Okay? So cells are constantly fighting entropy. Cells are constantly working to maintain order. One of the easiest ways to maintain order, or one of the clearest ways to maintain order, is to maintain concentration gradients. In this case, you can see that there are some protons, some hydrogen ions, okay, in here, but there's fewer of them out here. In this case, there's none. That's a gradient. Okay, so you can see over time, these will tend to flow downhill, or tend to flow out of the cell, until there's an equilibrium that's reached where they're the same. Okay, so again, this is intuitive, right? It makes sense that things are going to flow downhill and even out. That's just a fancy way, or rather, that's a general way of describing the second law of thermodynamics. Okay? On the left-hand side of the screen, you would say this has less entropy, this has more order, and this has less order and is more chaotic. Now, you might say, well, it doesn't look very chaotic. It still looks kind of even. Really, the point is, if there are differences you can observe, right? So you can see there's some here, but not here. If you can see differences, that means that there is order. Okay? And over time, those differences even out. So there is no more. Think about pouring cold milk into hot coffee. Over time, they even out. And you don't have to even put any energy into that. You can stir it to make it go faster, but if you do nothing, it will still even out over time. Okay? Just think of your bedroom. After a few weeks into the semester, you perhaps don't have as much energy to spend to maintain that order. And so over time, your bedroom starts to look a little bit more chaotic. You can describe this, if you want to be fancy, as a highly entropic state. Okay, so now that we understand the concept of energy and falling downhill and things moving from high energy to low energy, we can now talk intelligently about metabolism. So the metabolism is all of the chemical reactions in your body, and you can really divide them into two ways. You can say that there's the building reactions and the breaking reactions. There's catabolism, which is the breaking down, and the anabolism. One little fun way to remember that is think about what cats do. Cats destroy, right? Cats rip ferns, and cats rip drapes, and cats tear up carpets, and so catabolism is breaking. All right, so here's an example of a transformation that might occur inside a cell. We have reactants, okay, so A and B, and we have products, C and D. So you would say that A and B gets converted to C and D. Now, this might just be a generic chemical reaction that's happening in a test tube. If it's a metabolic reaction, what that means is that causing this to go faster and faster or inhibiting it would be an enzyme, right? Enzyme. Wow, that's really hard to write with a mouse, it turns out. All right, so a metabolic reaction is just a chemical reaction mediated by an enzyme. And so these reactants you can now call substrates. So substrates are reactants in a metabolic chemical reaction, or you could say a metabolic reaction. Or you can say a substrate is a reactant for an enzyme.